this leads us to two very important results. The first one is a result you'll recognize from calculus. It is the first derivative test. So that you have function f in some interval ab, continuous on ab. Let c be some point in the interior of the interval ab. Suppose that f is differentiable both on AC and on CB. Then, first thing, if you can find a neighborhood of the point C, it's completely contained in the interval AB, for which the derivative of the function at x is greater than or equal to 0 on the interval c minus delta c, and the derivative is smaller than or equal to 0 on the interval c plus delta, then f admits or has a relative maximum at x equals c. The second statement is basically the same. The only difference here is that we have f prime at x smaller than or equal to 0 on c minus delta and c, f prime at x greater than or equal to 0 on c plus delta. In that case, it is a relative minimum which is found at c. Are you noticing something here? We make absolutely no mention of f prime at c. All we're really talking about is that there is a change in the sign of the derivative at c, prior to c, after c. The function might be increasing, decreasing, or potentially decreasing, increasing, but we are not saying anything about the value of the derivative at the point where the derivative changes sign. And this is why in calculus, one of the things you might be interested in doing when you find critical points is to find not just the points where the derivative is equal to 0, but also the points where the function is defined, but the derivative does not exist. We'll prove one of them. The other proof proceeds sensibly the same way. Let x be some point in the interval c minus delta, delta. We're here. Know that the derivative is positive at that point. By the mean value theorem, you can find some point cx, which lies between x and c, and for which f at c minus f at x is equal to f prime at cx times c minus x. But we know that f prime at cx is greater than or equal to 0, because cx is between x and c, and by assumption over c minus delta c, which contains x and c for a small enough value of delta, the derivative there is greater than or equal to 0. So this derivative is greater than or equal to 0, which means f at x is to be less than or equal to f at c. Why? Look, this is positive. C minus x is positive because the way this has been built. X is in c minus delta. I wrote delta here, but it isn't. C minus delta c. So this term is positive. This term is positive. The product is positive. F at c minus f at x has to be positive, which means that f at c is greater than f at x. And this is true no matter what value of x you've picked between c minus delta and c. In the same way, f at x will be smaller than f at c if x lies in the interval c plus delta. So what have you really shown here? That fx is smaller than or equal to f at c for all x in the neighborhood around c of radius delta. It's true in the first case, it's true in the second case, so it's always true. So what we have, by definition, is that the function f has a relative maximum, x equals c. F at c is greater than f at x for all the points in the neighborhood. B, same type of argument. I want you to notice something else. This statement, this theorem, is not an if and only if statement. This is a clear directional statement. The converse is not necessarily true. Look at the following function. Here's a function whose definition or whose rule is 2x to the 4 plus x4 sine of 1 over x. X is not equal to 0, and 0 when x is equal to 0. I'm not going to try to draw this function. It's always problematic when we have the sine of something which sort of blows up to infinity here when x goes to 0. This function has an absolute minimum at x equals 0, but in every neighborhood around 0, there are going to be points, call them x prime and x prime prime, such that f prime and x prime is positive and f prime and x prime prime is negative. There's so much up and downness, oscillations. The behavior of the function is so crazy in terms of oscillation that you cannot help but have points where the derivative is positive and points where the derivative is negative. And that's sort of surprising, you know, but doesn't fit with our understanding of the derivative as a measure of the slope of the tangent line. Well, over intervals where the function is continuous, that's a good interpretation. But when you reach these funky points where it's not clear if the function is continuous at all, strange stuff happens. Okay? So one of the reasons why I don't do an awful lot of drawings using continuous graphs to highlight things, because analysis is basically a graveyard for these intuitions that we have about the way things work based on what we see on the chart. We follow the definitions. That's truly what analysis is. We can, if we want, give us a sense of direction by jotting or doodling things around. But in general, that isn't really a guarantee of a safe path. Keep that in mind. I'm going to end this section here with another one of these absolutely flabbergasting results. This is a theorem which is due to Darboux. It's insane. We have a function from closed interval AB to the real numbers. It is continuous on AB, and let's say that it's differentiable on AB. So far, nothing out of the ordinary here. Let k be some real number such that either f prime at A is strictly smaller than k, strictly smaller than f prime at B, or f prime at B, it's strictly smaller than k, is strictly smaller than f prime at A. So k lies strictly between f prime at A and f prime at B. Then there's going to be some point C in the interval AB, so somewhere between A and B, such that the derivative of the function at C is equal to k. What this is really saying is that the derivative of a continuous function, which may or may not be continuous, we have not shown that the derivative of a continuous function has to be continuous for the good reason that it doesn't necessarily have to. There are continuous functions with derivatives that are not themselves continuous, right? I mean, it's a possibility. So even though the derivative is not continuous, or at least not necessarily continuous, and there are examples where the derivative is not continuous, you can actually show, thanks to Darboux Theorem, that the derivative satisfies the intermediate value property, even if it is not continuous. That is just like mind-boggling. Absolutely. Let's do proof. I'm going to assume for this proof that the strict inequality that f prime at A is smaller than K is smaller than f prime at B. The other inequality is basically the same. Just relabel the variable. So we can do this without loss of generality. At G, be a function from the same interval AB to R, and we will define it as follows. X goes to Kx minus Fx. K is given, right? This is well defined. This function is continuous. Also, well, f is continuous, and k times x is continuous, and here we have a sum of continuous functions. So j is continuous. Great. It is going to be differentiable as well. How so? Well, f is differentiable, and k times x is differentiable. So the sum of k times x and minus f at x is also differentiable. Because g is continuous on a closed bounded interval, by the Max-Min theorem, there's going to be some point C somewhere in the interval AB, such that g at C is maximum value that g takes. This is not necessarily the case if we have an open interval here, or if g is not continuous. Now we do know that g prime at A, computed directly, this would be k minus f prime at A. This is positive by assumption here. So what this tells us, C is not equal to A. Why? Well, if we do have the maximum value and the function is differentiable, then g prime at C should be equal to 0. Which we have here is that g prime at A is not equal to 0. So C cannot be equal to A. In the same way, compute g prime at B, and get k minus f prime at B is negative. C not equal to B. C was equal to B, g prime at C would have to be equal to 0 on account of C is where g reaches its maximum, global maximum. So what we have is that g prime at C is equal to 0 for some C in the open interval AB. So g prime at C is equal to 0 for some value C in the interval AB. But we know what g prime at C is. It is equal to k minus f prime at C. Given that it's equal to 0, we conclude that f prime at C is equal to k. Give me any k between f prime at A and f prime at B. Strictly, I can show the existence of a point C somewhere in the interval AB, which will guarantee that f prime at C is equal to k. Flabbergasted.